All right, welcome. As your finance tutor for this explainer, we're going to dive into something every analyst has to deal with. See, we spot patterns in the market all the time, but how do you know if that pattern is a real money-making relationship or just, random luck? Today, we're going to build a super practical guide for testing these relationships, pulling straight from Learning Module 9 so you can make these calls with real confidence. So let's kick things off with the big question, right? You're looking at a chart and it seems like a fund's returns are moving with the S&P 500. It looks real, but is it? Is it statistically significant or is it just a fluke? Honestly, being able to answer this is what separates a good hunch from a great analysis. So let's break down exactly how you do it. First things first, before you run any fancy tests, the most important thing you have to do is just look at your data. What kind of information are you actually working with? Because the answer to this one simple question is going to send you down one of two very different paths. And here they are, those two big paths. On one side, you have continuous data. Think of these as your numbers, things like stock returns, interest rates, stuff you can measure. And on the other side, you have categorical data. These are your labels or groups, like is it investment, value, or growth? Is an ESG rating high or low? The test you're going to choose depends completely on which of these two buckets your data falls into. Okay, so let's head down path 1. This is the one we take when we're dealing with all those numbers. And what we're trying to do here is measure the relationship between two sets of that data. In the world of finance, we have a name for that. We're looking for correlation. So for this job, the standard tool we pull out of the toolbox is something called a parametric test. Now, parametric sounds complicated, but all it really means is that the test has some ground rules. It assumes your data behaves in a certain way, usually following that classic bell curve you've seen before. These tests are super powerful, but, and this is a big but, they only work if your data is playing by those rules. So what are we trying to accomplish with this test? Well, it helps us figure out if the correlation we're seeing in our small sample, say the last 3 years of returns, is strong enough to mean something for the entire population of returns, past, present, and future. It's about moving from a small observation to a big conclusion. And this 6-step process here, this is our playbook. It gives us a clear, repeatable framework. We start with what's called the null hypothesis, which is basically the default assumption that there is no relationship. Think of it like a courtroom. A relationship is considered non-existent until proven otherwise. We then go through the rest of the steps to see if our data has enough evidence to overturn that initial verdict. Now, this formula right here, this is the engine that drives the whole test. It looks a little intense, but you're really just plugging in two main things. R, which is the correlation you found in your sample, and N, which is just how many data points you have. The formula cranks through it and spits out a single number, our T statistic. That one number tells us how significant our finding is, and it's what we use to make the final call. Okay, but here's the reality check. What happens when the data breaks the rules? Because let's be honest, real-world financial data is almost never perfect and clean. Market shocks happen, you get crazy outliers. So when our data doesn't fit that nice, neat bell curve, what do we do then? When our data gets messy and doesn't cooperate, we have to reach for a different tool. And that's where non-parametric tests come in. Think of these as the Swiss Army knife in your toolkit. They're designed to work even when the strict assumptions of our standard tests just aren't met. And the solution is actually pretty brilliant. Instead of using the raw numbers, which can get totally thrown off by one or two extreme outliers, we do something much simpler. We just convert all the data into ranks. First place, second place, third place, and so on. By focusing on the order instead of the values, the test becomes way more robust. And the process itself is pretty straightforward, as you can see. You rank everything for variable 1, you rank everything for variable 2, you find the difference in the ranks for each data point, and then you plug all those differences into the final formula to get your answer. See what's happening here? We're not even looking at the raw return numbers anymore, like that 2.453%. Who cares? All that matters now is the relative position. Fund A had the 27th best return that year. Fund B had the 31st. The test is now looking for a relationship between these ranks, not the actual value. So the takeaway here is super simple but really powerful. Always check your data first. If it's clean, it follows the rules, great. The parametric t-test is your go-to. But if it's messy, if it has some wild outliers, or if the data is already in ranks, then the Spearman test is absolutely the right tool for the job. All right, so we've handled the numbers. Now let's explore that second path. What happens when our data isn't numbers at all, but categories or labels? In this case, we're not looking for correlation. We're checking for something a little different called independence. Yeah, for this, we need a completely different kind of tool. It's called the chi-square test. It's designed for one specific job, to see if being in one category is independent of being in another. For example, is an ETF's size, like small, medium, or large, completely unrelated to its investment style, like value or growth? You know, the core idea behind this test is actually really intuitive. We just compare what we actually see in our data to what we would expect to see if there was absolutely no relationship between the categories at all. If there's a huge gap between what we observed and what we expected, that's a pretty big clue that the two are related. And this is our starting point. It's called a contingency table, which is really just a grid that counts things up for us. For instance, we can look in the table and see that we observed exactly 42 ETFs that were both small in size and growth in style. This is our observed data, the facts, straight from the market. So this is where the test does its work. It calculates what we should have seen in each box if size and style were totally unrelated. For that growth small category, we actually saw 42 ETFs. But if it were just random chance, we'd only expect to see 34. The test basically measures the size of that gap for every single cell in our table. And this formula, which might look a little scary, is really just the final step. All it's doing is adding up all those individual gaps we just calculated, and it boils them all down into a single number, a single test statistic, the chi-square value. That one number tells us the total amount of difference from what we expected. Okay, so let's zoom back out and put all these pieces together. Think of what we just built as your practical, go-to decision toolkit for testing relationships in pretty much any dataset you're ever going to face. And here it is, your entire decision-making guide in one place. It all starts with that first question. Is your data numbers or labels? From there, you just follow the path. This simple process makes sure that you always choose the correct test for the job, which makes your final conclusions solid and dependable. And that brings us to the crucial next step. Look, knowing that two things are related is powerful. It's a huge first step. But the real value for an analyst is being able to model that relationship to make forecasts about the future. And that, well, that's the world of regression analysis, which is a whole other topic. But for now, you have the essential tools to figure out if a relationship is even worth looking at in the first place.